Good evening, everybody. Thank you for joining in and being a part of this evening. This is Sonali Chauhan on behalf of TCS ION, and I welcome you all to this masterclass where we'll talk about Pipeline ADCs with IIT Hyderabad. In today's fast evolving tech ecosystem, the need of high performance, energy efficient, and compact devices is driving innovation across industries. At the heart of this transformation lies VLSI, which is very large scale integration, enabling the creation of powerful system on chips, which is SoC design. In this exclusive masterclass on Pipeline ADC, in collaboration with IIT Hyderabad, will take you through the essentials of modern analog design, focusing on how Pipeline ADCs plays a critical role in application spanning mobile technology, healthcare devices, industrial IoTs, and beyond. This webinar will provide an overview of Pipeline ADCs covering their working principle, stage-by-stage operation, and essential building block such as sample and whole circuit, residue amplification, and digital error correction. So in this session, the key highlights are fundamental of analog IC design and its link to ADCs, architecture and working of Pipeline ADCs, design and flow, and challenges in building Pipeline ADCs. So whether you are a beginner exploring the field or someone looking to build a strong foundation, this masterclass will equip you with essential knowledge to navigate the world of semiconductor design. We are honored to welcome Professor Ashudeb Dutta and Mr. Pradipta Ghosh from IIT Hyderabad, who will be leading this insightful masterclass. And with their deep expertise and experience, they will warmly guide us through the fundamental of VLSI chip design, touching upon Pipeline ADCs and help you connect theory with real-world application. Let me introduce both of you to all lovely audience. So Ashudeb Dutta is a professor in the Department of Electrical Engineering at Indian Institute of Technology, Hyderabad. His area of research included analog and radio frequency IC design. Mr. Pradipta Ghosh, he's a MTech research assistant in microelectronic and VLSI at IIT Hyderabad. His research interest in analog circuit design. So again, very warm welcome to both of you. So Ashudeb sir, before we dive into the core of today's masterclass, we would like to understand from you that in the electronics and semiconductor domain, there are several specializations shaping innovation today. Could you share where VLSI stands in terms of importance and relevance, and particular why analog and mixed signals and ADCs, especially Pipeline ADCs, are so significant in current context? Over to you, sir.
So, students, thank you. Good afternoon. So what I want to say, the world is digital. As you know, everything, whatever mobile or whatever image or whatever voice, all you are talking in an analog form, but finally it will be digital. So some process is required will be convert this analog to a digital form. What is the beauty of the digital thing? Because it is only two-level signal. It is not a multi-level signal. And secondly, when you are taking the two-level signal, your operation and your gate count, those should be very, very high, so that you can computationally, you will be strong. So all the Snapdragon processor or the Intel processor, or if you go to any other AMD processor, all will be count in the digital. But whatever I'm talking today, or whatever image you are seeing us, all are analog domain. So you have to convert. In that process of conversion, first you have to do some mode, how will be convert. That Pradipta will be explain you one by one. First process is the sampling, and then quantization, and then digitization. So this level of digitization, sampling and quantization. So sampling and quantization is the common process for any case of a analog digital conversion. But this digitization process have a multiple form of there. So one of the form is the Pipeline ADC, and other form, multiple other form is there, which Pradipta will be give you. But this Pipeline ADC help you to be parallel processing. like you had in the computer science or any other task. Suppose you want to do, your one hand is there. You want to drive a car, you need a two hand. So parallel processing has been done in a pipeline mode, and so that it will be faster. And whatever application you see, video, image, or any kind of RF kind of application, like communication application, you have to enter through the pipeline ADC because it has a high resolution and respective speed also good. So now I'm like, whenever you go through the details of that, you'll be understand some of the insight through how it is moved.
Thank you so much, sir. Thank you so much for wonderfully answering this question. And Pradipta, sir, would you like to add something with on this?
Yeah, thanks all, and good afternoon to everyone. Like as sir already mentioned, so the requirement of the digitization and from the analog world, we always need this digital procurement and the digitization part to drive our systems and everything. Now, where comes this pipeline ADC and what's its beauty is like it's nothing but simply resource sharing. Like if some work from some place to another place, if one work has to be done or one thing has to be sent, like two things we can do. Like one thing I am taking, and like a person is taking one thing and like carrying that thing to the another place. But the pipelining concept is nothing but like if we in between the two places, if we place 10 people and all of them work along together parallelly, then the process will be so much fast. Obviously resource in terms of resource sharing we will need more resources, but the speed enhances drastically. So that's the beauty of pipeline EPC. I will explain the more of the overview and how the processes are done over there in the further parts of the webinar. Yeah, so from my side I can add this.
Great explanation. Audience, before ado, I would like to because already both the sirs have already set the context about pipeline ADC. So, with the encouraging note, let's now explore this subject in greater depth. And over to you, Pradipta sir. Please take us through the masterclass.
Welcome to this masterclass webinar, and I am Pradipta Ghosh. Currently, I am working as an analog design intern at MediaTek, Bangalore. I have done my schooling from Kolkata, West Bengal, and my schooling and both my BTech from Kolkata, West Bengal. And currently, I am pursuing my MTech research assistant from IIT Hyderabad under guidance of the Professor Ashudeb. So let me delve into the mm, mm, just- hmm. Yes. So now I will go into the details of this ADC and how it works in the real world. So as I've already mentioned, so ADC is actually bridge between the real analog world and the digital domain of our daily use, like our mobile phones, our laptops, our any device we use. They all are driven by this digital data, but from our real world analog data only come. So we need to reach upon that bridge between them, and there comes the usefulness of this ADC. So what I will do here, I will just outline the structure of this webinar as like I will begin with this fundamental of this ADCs, then I will move to pipeline ADCs, focusing on mostly the 1.5 bit per stage architecture. And like I will finally, like in last some few minutes, I will share some of my own design thoughts and own, like when I designed and how it came through. All those like a little bit of overview I will share finally. And like we want to by that I think we will get a good overview of like how it is actually applied in actual design. So yeah, this helps this like establish relevance right from the start. Yeah. So as per the ADCs are concerned, in this there are few types of ADCs. So those are like flash ADCs, SAR and pipeline Sigma Delta. Those are like a few different ADCs are there. And the thing is like both of all of the ADCs have their own advantages and have their own disadvantages. So pros and cons, like if you come to pros and cons, so flash ADCs are like they're extremely fast in this data conversion, but they are very much power hungry. Like if we think about this flash ADCs, like you can think something like that, like for each set of bit and for each set of bit conversion, you are using like one resource to convert that data. So what comes through it, you are doing that conversion very fast. As like for 10-bit conversion, you are using so many of resources. Like there are some formula regarding like if 10-bit conversion is there, we need the flash ADCs are mostly comprised of this big comparators. So now if we are using 10-bit of flash ADC, we need something like to the power 10 minus 1. So what comes roughly around 1023 comparators. So if we are thinking of 1023 comparators, they will take so much space and they will take so much power on chip. So but the conversion is literally like it's like the name itself is flash, because its conversion type is very flash. Like it light first conversion it can give. So that's the main advantage of flash ADC, and power hungriness is the disadvantage of it. And if we come to this SAR ADC, SAR ADC are like it's simple. Like its architecture is not like its conversion rule is very fundamental. Like how it works, it works only on one comparator, and like each stage by some capacitor DAC, CDAC, charge sharing, and charge reformation and all. We use one comparator, and by each clock stages we convert one bit, and then again it's a like reiterative process. Like you can from an overview type of thing, you can think something like this. Like you need something like you have your LSB from like your lowest available minimum voltage something 0, and if your highest available minimum voltage is something 15, let's see our full scale range is from 0 to 15, but you are given with a data of something 10 10. Now you need to convert this 10 to some digitized data using SAR EDC. So what will be your fundamental process to do that? So SAR EDC like fundamentally works on this like binary search. I think many people are there from computer science and other backgrounds, and also like any engineering background students will fundamentally know about this binary search method. So it works on that fundamental principle of data only. Like if you're given with that in the given example as I was telling, so if you're given with this 10 volts of 10 volt of data, and your full scale range is from 0 to 15, so what SAR EDCs will do, it will check, it will whatever the range you are available with, it will divide that range into two halves first, like as a one upper half and one lower half. Now in the upper half it will fall between like this 9 to 15, and in the upper lower half it will fall between 0 to 8. Now what will it will check the given input data like 10, is it in it's in which half, it's in 0 to 8 half or it's in the upper half. Now accordingly like as it's in the upper half like 9 to 16, so it will check, okay, 9, so my first bit comes into that according to the upper half, so my first bit is 1 as it is more than the half stage. So then it will check between, as now we are in the range of 9 to 16. Now it will check like, okay, now the 9 to 16 range, it will be divided into two halves, like 9 to 12 or 9 to 13 and the 14 to 15 or 13 to 15 like that. Now it will check like 10 comes into which half. If it comes in the lower half as it is, so lower half, so it will switch the second bit as 0 as it is the lower half. If it is the upper half, it will switch the bit as 1. So if it is a 5-bit SAR ADC, how it will do? According to this binary search, at every step it will take decision of every bit, and it will tell, okay, what is the equivalent 5-bit conversion of that input data. So that's how it works. It's a very simple kind of thing, and as one comparator we are using in a flash ADC for 5-bit, we need some 2 to the power 5 minus 1, but it is something 31 comparators we need. But here we, by using only one comparator, we can do the whole conversion process. So it's simple, and it's very much like power budget is friendly in case of them. but the point is slow. It's like, as it is only one conversion per clocks, so it's very slow. It's not like flash. It can't give so fast conversion rates. So there's the problem of this disadvantage. Not problem, I would say. It's a disadvantage. And if we come to this pipeline ADC, so pipeline ADC is like, it's a balance between them. It's a balance between this both flash and SAR ADC. So how it is like, it offers us a reasonable like speed and resolution. Like how it will do, it won't use like so many computers like flash ADC, but it won't also like, it won't be done within one computer also. So it will go to some mid gap. Like if it is instead of 1023 computers for 10 bit, we will need some very less, like some 20-30 computers, so it also work according to our design. Like it's 1.5 bit per architecture or 3 bit 2 bit per architecture. Accordingly, that we will need our number of computers. So there it's advantages. And as I've mentioned, like some of the applications of this pipeline ADCs in the real world, if we say our real world, so communication in our all the communication fields and all these 5Gs and all 6G communication fields nowadays. So we are going to this gigahertz range of in real world. So in the communication field, in the medical applications and all the IoTs and automotive applications, so these are this role of this pipeline ADC is very instrumental there. So if I go into a little detail for this pipeline ADC, so what can I tell? As I was mentioning earlier in the slide, like the pipeline ADC is motivated by these shortcomings of the other architectures. That's why it came. It came to solve the bridge between the other two ADCs you can think of in a very fundamental way. So the like poor resource management of the flash ADC and like the higher amount of comparator counts for each bit, its impracticality of the design, and with comparison to the SAR bits, one bits resolution per at a time. So this things pipeline is like split the conversion into stages. How it does that? How it like uh, fills up this bridge or fills up this gap between those two kind of ADCs. It it the pipeline ADC does the conversion in stages. Like each stage will solve a fewer number. Like for 10 bits, we won't go to convert our 10 bits at one go directly. So what we will do, per stages we will convert it. So like for instance, we can say for like 10 bit, as I was telling, some 1023 normal comparators were needed, but it will do like it will do 2 bits or 3 bits per stage first. Then whatever the data comes from the first 3-bit stage or first 2-bit stage, that data it will get again converted in the next 2-bit stage. Now whatever data comes from the next stage, it will go to the subsequent stages. So like that, only within 4, 5 or 6 stages we can convert the whole data. So that's the whole point of pipeline ADC. So now if you think, instead of doing the 10-bit flash ADC, if you are using 10-bit pipeline ADC by this 2-bit per stages, so how it helps us? So 2 bits per stage means you need only, like if the simple architecture, in the 2 bits per stage you need only 3 comparators. So and if you use such 6 kind of stages, so your work will be done within like 20 comparators. You won't need 1023 comparators. So that's the main beauty of this pipeline ADC architecture. And that's why like currently it's used in this wireless and imaging industries. Yeah. So like going deeper into the working principle, like the pipeline ADC's conversion rule or conversion uh, process, there's a like very important terms in this pipeline ADC conversion business. It's like this residue conversion. So it works upon this residue. So fundamentally, I will explain this residue like in such a way. You can think it of some like that. You remember, I just mentioned this RADC thing, like it uses this binary search method for this conversion. Now, in case of this pipeline ADC, how it converts, let's take the previous example on, like you are given it 10 volts. Now, what it will do, first, like you are given with in Pipeline ADC at first stage. Let's say you have 2 bits of the conversion like mechanism. So for 2 bits of conversion mechanism, it will convert this 10 volt to equivalent 2 bits of binary equivalent. I think like anyone has any question, or like should I slow it down? Anything,
Sir,
or
you can
I
continue.
can.
You can continue.
Oh, okay. Oh, okay. Yeah. So so what I was so what it will do, do first, it will take the 10 volt data, and it will do first 2 bits of conversion. So instead of 10 volts to like 10, instead of 10 bits, it will do 2 bits of conversion. And let's say for 10 bits equivalent, it will give us like 10 as our data input, like as our digital output, 10. Now accordingly, this 10, like if you think of this, 0 to 16 was my voltage range, but you are given with only 2 bits of conversion data. So what are your levels? What are your levels of conversion? So your levels of conversion are 0, then 4, then 8, then 12, then 15. So or 16, like what were the 5 level of conversion. Now converting it, you are giving this 10 volts of data. So what it will do, it will give you digital bits accordingly, like 8 or 12. Mostly, like we can assume if we are taking it as 12. So it will give you the digital bits accordingly 12, but your input data is 10. Now what we are fundamentally trying to do in the subsequent stages, whatever the digital bits you are getting from 12 from 10 with respect to 12, so that's analog. If we are again changing, like if we are again crossing the domain from digital to analog, 12's digital equivalent is 12, analog equivalent is 12 only. Whatever the 12 digital binary thing was there, that's analog equivalent is 12 only, but your input is 10. So we will subtract that thing. We will subtract the original input voltage from that digital binary equivalent of 12, or the whatever the stage was there, like 12 to 10, we will subtract it. So we will get we will get a remainder, like remainder type of thing. That remainder in here is called this residue. So that 2 is our residue, which is got from 12 minus 10, we are getting 2. Now we will send this residue to our next stage, and again we will convert for 2 bits conversion. Again we will convert for 2-bit conversion. Again one digital bits will come. Again we will subtract it for the residual, and again we will convert it. Now there is a catch. Like if anyone like to answer it, like I will first like ask this question, if anyone can answer it or think it here. So I will later I will explain, obviously. Your whatever the ADCs you are using, remember for each stage you are using the same ADC of 0 to 16 only. That range is the same, 0, 4, 8, 12 or 16. All the ranges are same. But from the first stage, in case of 10 volt of input, 10 millivolt or 10 volt of input, you are getting residue of 2. Now, when we are sending in it to the subsequent stage, in the next stage, the pipeline ADC, or the whatever the mechanism of the ADC is there in the next stage, will it be able to like convert it directly? Like, what do you think? We are talking here about this conversion per stage, like stage by stage conversion over the residues. So from the first stage we are getting residue of 2, and again we are trying to convert it. So if we are sending this 2 directly to the next stage, we will be able to convert. Like your residue was only from 12 minus 10, you are getting only 2, but your ADC's ranges are like accordingly 0, 4, 8, 12, that only. So the subsequent stage, the next ADC won't be able to recognize the residue input. Whatever the residue input you are feeding through, it won't be able to recognize, because it's too small for that ADC input range. So that's where the thing, or that's where the concept comes for this residue amplification. So this residue amplification is done with our like known, so there are known amplifiers for us, or this normal any amplifier you can think of, but generally we use some high gain, high uh, bandwidth amplifiers to convert this residues, or to multiply or to amplify these residues. And then we again we like do our this conversion business. The say like the subsequent process is same, everything is same, only this multiplication is added for this residues. So this multiplication and amplification is done over the residue, then we will convert it. So this residue conversion and amplification done in a whole package or in a whole block. Like this is called like this multiplying DAX or MDAX in our language. So like why this multiplying DAX? Like DAX for this, I told you that whatever the digital bits we're getting from each stage, that you need to first convert into analog, and again for subtraction part. So that thing is for DAC, and M is for multiplying. So from this multiplying DAX come, MDAX come. Now comes like for the digital backend part. So output from all the now outputs from all the stages, all the stage output bits are collected from all the stages, and that collected stages, like those are concatenated, like it's are like those are before like the final conversion is done, like they're collected and they're connected to form a final digital code. Like while the first conversion takes a few cycles, then only the pipeline starts to filling, and we get a digital output per cycle, ensuring that for this, like our throughput is very high. To ensure that thing, our throughput is very high. So yeah, this is for the applications, and that's why this pipeline ADC's resolution and speed both are in a side of like balanced conversion rate as used for our this communication receivers. Yeah, we were at this digital error correction and this working principle of this pipeline ADC. First, this stage by stage conversion, then this residual amplification, and this digital collection of bits and concatenation of all the bits together to get my final output. So this is the whole working principle in one go. But if we go step by step, so there we first, whatever the analog data is available with us, we need to first make it to use for digitize something. First in first is needed. So there is difference between analog data, discrete in time data, and discrete in time and amplitude both. What's actually called digital data. So what is discrete in analog data? Analog data is it's in time domain, and in amplitude domain also it's continuous. But in discrete data, discrete in time data, those things are not like it's those things are not discontinuous in amplitude domain. Those things are continuous in amplitude, but those things are discontinuous in time domain. So those discrete in time data is called sampled data in our language, and that thing needs first sampler. So in case of this pipeline ADC, so the sampler we use typically switch capacitor circuit. Switch capacitor circuit is again a very important application of this in this circuits and analog circuits and mixed signal circuits domain. So switch capacitor circuits are like based on this principle of first hold, like first getting or sample the charge and then to send the charge to another node. So this switch capacitor circuit actually plays an important role in that concept. Yeah. So if we come there, so what this switch capacitor circuit in terms of sampling do? So this captures first the instantaneous value of the analog input at a precise clock cycle. Like we have the clock cycle for in mixed signal, everything, or in mixed signal in digital, every operation you do on the edge of clock. Like there are two types of clock edging, or either clock triggering. Either it can be edge triggered or it can be like level triggered. So mostly in our applications we do it like any edge triggering, like it's either positive edge triggering or negative edge triggering of the clock. So everything is done, every operations, be it sampling, be it like this MDAC conversion, be it sending to the digital digital logic bits, everything is done in the edge of clock. So yeah, so the instantaneous value is getting like sampled at precise clock edges. Then low in this case also, this like jitter and those things of the clock comes into picture. Those things are very detailed, I won't go much there. So yeah, so we need to the switch capacitor circuit work very accurately to make our to like sample our data properly. Like there should not be any like you can understand it in this way. Like you are some 100 millivolt data input you have. Now you want to digitize it into some 12 bits. Now 12-bit digitized data means, like if your range is some 0 to 1.2 volt, your full scale range. So if you are having 12 bits of digitization, so what's the resolution comes along? Resolution comes along nearly some 200 on 300 microvolts. Like it's 1.2 by, if you're getting this 2 to the power 12, 1.2 by 2 to the power 12, you are getting some 200 microvolts of resolution per bit, or sorry, per stages. Now your sampling and hold, if it is not working properly, and instead of 100 millivolt, if you're sampling 101 millivolt or 102 millivolt or 99 millivolt, so itself the error comes in the sampling itself. So there is no point of digitizing it in further. So you are already incorporating it. So this sampling has to be very precise. Like 100 millivolt, you need to sample it very properly first of all. Yeah. So there this accuracy comes in the part, especially in case of this high frequency inputs. Yeah. So now the like function of this quantizer, it like it maps that sampled analog value to its like nearest discretized digital level. Like as I was telling, like for 0 to 15, if you're taking 10 volt input, your nearest digital level was 8 or 12. 8 or 12 was your nearest digital level. So you need to quantize it according to the level of 12. Okay. So now the resolution is set by the number of quantization levels you have, and that directly impacts the like ADC's enough. So there is a very like important measurement parameter of this ADC's working. So that is called enob in like it's actually abbreviated form of this effective number of bits. So when your all the conversion is completed, so how many number of, you are aiming for 12 bits of conversion, but you are getting let's say after conversion there are obviously non-idealities will be there in every design. So due to that you are getting how many number of bits effectively, so that counts for this enough. And together all these components, so this input signals like quantization noise, thermal noise, all these things when you are incorporating in our design, so all these things will give us final resolution of digital bits at some like speed, whatever the frequency input frequency you are using for. Okay, so going to like next thing. So if I describe this flash ADC like in a little detail. So flash ADC, what it does, it uses this parallel comparators for all levels. So you can think it of such a way, uh, like you have some input voltage and you have some specified number of, according to a number of bit, you have some specified number of comparators. Now what it does, so it will every comparator at one go, all together, like all simultaneously doing this all together, every comparator will like at one go means at one single clock cycle this will happen. At single clock cycle every comparator will compare your input voltage, like level of your input voltage, or some fraction of it. It is a design part, let's leave there. Let's understand the concept here. So every comparator will compare the input voltage part with its own threshold, and it will make a decision like your your input voltage, if some levels you can think of your input voltage. So now accordingly every comparator, if a like you every one of you know, I think this resistor divide, normal resistor divided circuits, like we study at this our like school on. So like whatever the voltage range you have, you're taking some resistor dividers into it. And like so 1.2 volt like starts from 200 millivolt, 400 millivolt. So at every node 200, 400, 800, 1 and 1.2, so like that it happens. And my comparator is connected at each node, each comparator is connected at each resistor node, and we're comparing the voltage is higher than the comparator threshold or not. That what we're doing in a short. So now you're taking some 800 millivolt, but you are comparing the like below most comparator, so your output will be obviously lesser than this comparator threshold, so it will give me output bit of 0. Now the above one will also give 0, its threshold is only 400. 800 it will give 1 but 1 volt it will give 1, because 1 volt is greater than 800. Like that will give you some like 7 comparators will give you 7 number of output data. So those things are called like this thermometric codes. Now this thermometric codes like there is a thing called in our digital logic, like the using K maps or any other conversion techniques, we like convert the thermometric codes into binary data, and we use in further cases. But yeah, the problems are there. Plenty of problems are there. Like let's go for the like advantage is, as I was mentioning, all this comparison is happening in a single clock cycle. So you think in a single clock cycle you are getting all your converted data, so it's very fast. It has to be very fast, as it is doing in every single clock cycle. But in case of practical issues, there will be this comparator counts will grow like exponentially with number of bits. Like you are using 3 bits, you will need 7 comparators. You are using 4 bits, you will need 15 comparators. You are using 5 bits, you will need 31 comparators. You need 8 bits, you will need 63 comparators. So you can see in case of like if you're using 16 bit, 16 bit of ADC, if you are using flash ADC, so it will require, if I calculate correctly, something like 65,535 number of comparators you will need. In case of 16 bit of conversion, so you can see, so it's comparator sizes are growing exponentially. But in case of our chip, so there is a given area, you are given with the area, you can't go beyond that. So yeah, so comparator counts and area will increase exponentially, and the number of comparators will use, these comparators will be power hungry, and it will consume a lot of power. So yeah, here you can also see this large silicon area required. So everything is about area and cost in our business. So and obvious, and also there is a non-ideality incorporated with these comparators. These comparators have its own offset mismatches, offset errors or offset mismatches, which what it does, like it then it compares incorrectly, and it will give you wrong thermometric codes, which will subsequently will give you wrong binary data. So like that, there are disadvantages also there. Oh, it's okay. So going to this next part, so motivation of multi-step converters, these things I was actually uh, describing initially only. So like I will read through this ones, like this flash converters, as I told, like number of bits, area and power consumption is like same practical kind of design beyond 7 to 8 bits. You can see the exponential it here. 2 to the power 7 and 2 to the power 8 will need some 63, as I was telling, not 63. I think 255 to the power 8 for 255. Yeah. So multi-step conversion is done, and here this like conversion is done with some like coarse conversion and fine conversion. So you can think like that. If I put it in such a way, like multi-step converters like break the process into coarse and fine steps. Like for example, like a first stage may perform a rough conversion, like it won't be so precise. But while we are going towards the subsequent stage, second stage, third stage, it will refine the residue, and the residue, like number of comparators and total power, it will like go beyond more fine and fine and fine. But this multi-step design have its own design challenges, and like it needs more error handling, more imperfection, and more in case of this design language. And so there is again one concept comes in terms of this redundancy. So redundancy like helps us by making like later stages capable of correcting earlier errors. Like you are in conversion, like let's say stage one, you are committing some error, you are committing some error in the conversion. But if you are having this redundancy in your bit conversion, it will help you, like it will help you correct that error in the second stage, third stage, and fourth stages. And so this combination of this efficiency and speed like motivates you for this pipeline architectures actually. Yes. So this is the like a basic block diagram kind of thing what I have put in here. So you can, if I go through in it, I can just tell you as I was telling. So you can see this V in the input voltage here. Input voltage here. So input voltage here is coming from this coming into the sampling and hold circuit. This is S/H. That's the sampling and hold block. So input voltage you are coming here. So it is getting sampled and hold here. Now the same thing is going through this like the like lesser number of bit ADCs, like 2 bits or 3 bit ADCs. You will need some basic flash ADCs, like 2 bit flash ADC. You will need some 3 comparators only. So these 3 comparators will have you can see it. So this ADC will convert it with for m bits, it will use 2 to the power m minus 1 comparators. And with this reference voltage, it will convert it to m bits. Now, as I was telling, we need to subtract it. So this will go to this DAC, and this DAC and the original input voltage will be getting subtracted through the subtractor. And this VQ is my residue voltage. This is called my residue. And this residue voltage is again getting multiplied with this 2 to the power m. Now, there are so many catches, like how this 2 to the power m is getting decided. So the maximum value of what gain you can use here. Why is my cursor is going? Yeah. So what the maximum gain you can use, it has to be 2 to the power m on. I think something is coming. Yeah. So this has to be this 2 to the power the maximum gain you can use for this amplifier is 2 to the power m. Whatever the m number of bits you are using, if you are using here 2 bits, so you can use here gain of 2 to the power 2 only, maximum. Otherwise, it will give you an error. Why error? Like in simple language, if I tell, if I use instead of 2 to the power 2, if you are using 2 to the power 3 or 2 to the power 4, like instead of 2 square 4, if you are using gain of 10, your residue voltage by default will go beyond this ADC's full scale range. So you won't be able to convert it again. So the ADC will saturate. The basic thing is this ADC will saturate with that. And now this residue voltage is again we are giving to a new like sub-range ADC, and again we are getting some K bits. And if you see this digital error adding, so here the first stage we are getting, here I am just showing the two-step conversion. It will be multi-step actually in real. So here from the first stage you will get some M bits, and my cursor is so yeah, in the first stage you are getting some M bits, and in the like next stage you are getting K bits. So what we'll do this concatenation here. So M bits plus K bits will give you the final final number of output. M plus K will be your final resolution. So that's how in a nutshell it works. Here the same things actually I am putting again and again. So here you can see this amplify VQ to get the full range of second. So yeah, so final output, yeah. So here you can see this ADC output is M, and Y this K transition, and this V input is actually this formula comes over here. If you do it hand, it's a very basic block level calculation. So this V input output voltage is actually calculated using this K by 2 to the power K into Vref. This is the like from bits to analog voltage conversion formula. So this V input formula comes over like that, and this resolution accordingly comes this M plus K, and this N output voltage is 2 to the power K into M. So these are the formulas. This is just formulas. I think concept you have got already. Formulas you can see anywhere, any paper or any book you can see, and you can understand how the formula works. Okay, so let me make it faster. Yeah. So sub ADC and redundancies, like I will explain here the role of the sub ADC, and this like each stage uses a sub ADC to resolve only a few bits, passing the residue to the next stage. As I was telling, redundancies introduced like to what it does, it tolerates the comparator offsets. Like there's a comparator offset, I was telling in design offsets will come. Now the redundancy part, it will tolerate the comparator offsets and other like the imperfection like mismatch offsets and all. So this overlapping decision range allows this digital correction logic to recover the correct final output even in the presence of small errors. So together this sub ADCs and redundancies form the foundation of this whole pipeline ADC. So yes, this here it is written also. So this tolerance of the comparator offsets and the digital error correction is handled by this redundancy concept. Okay, so if I go here, digital error correction, same. I think here I am writing. Yes. So yeah, same. So what like just a basic example of this. As I was telling, maximum you can use here 2 to the power m. Like here, as I was telling maximum you can use the gain of 2 to the power m. Now to like mitigate the comparator threshold offset threshold errors, what we instead of 2 to the power m, what we use actually a gain of a little low, so 2 to the power m minus 1. In terms of this redundancy concept, I will come to this, like it's a special kind of architecture of like 1.5 bit per stage architecture. So what it does, each stage in a like 1.5 bit design uses, like instead of in 2 bits design you needed 3 comparators, but in case of 1.5 bit you will need just 2 comparators. So dividing the input range not in 4 ranges, in 3 ranges, because you are using 2 comparators. So three regions you will divide your input range, and now effectively like resolve 1 bit plus redundancy. It's like 1.5 bit. No, so it's 1 bit plus the redundancy of 0.5 bit. So that way it works. So redundancy ensures that the small comparator errors do not corrupt the output, because like in case of 2 bit, you would in the next stage you would give a gain of 2 to the power 2 like 4. But in case of 1.5 bit, as it's effectively 1 bit, so you will give a gain of 2. So the whatever the residue voltage is, that won't be multiplied by a larger value. Like it won't reach out to the ranges of your ADC. So that's how it works. Redundancy works. So I'm telling it very superficially, because like if I have to explain it, actually I need a like board and pen and board. So just explaining it overview. So digital error correction can fix that way. So this reduces this analog design challenges of this offset correction, mismatch correction, whatever those things. This reduces and make our design more robust. So nearly like 10 to 14 all pipeline ADCs, whatever the big pipeline ADCs, 12-bit, 14-bit, 16-bit. So general architecture of them is just 1.5 bit per stage, mostly. They use it, this one. And actually it's a good balance between this speed, accuracy, and the complex design architecture, the language all over this. So by using this redundancy, we can like avoid this strict precision, and obviously it's very handy to use. That's what I can tell. Yeah. So if I go to the next one, so like so I'm here I will come with little bit discussion of my design. So what I designed 12-bit pipeline ADC with 1.5 bit per stage. So and my supply voltage is actually 1.2 volt supply voltage, and finally it will be taken from this either LDO or DC-DC converters. The power supply of this ADC will be driven by that. And the architecture is simple. As I was telling, 1.5 bit architecture is effectively 1 bit, so we will use 10 stages of those 1.5 bit architecture. So effectively 10 into 1, 10 bits you will get there. And finally we will directly use a 2-bit flash. So just 2-bit flash, so it will just need 3 comparators. And in the 1.5 bit, every stage you will need 2 comparators. So 10 stages into 2, 20 comparators, and lastly 3. So 23 comparators will do your job. And so like that is coming. So 10 into 1, 10 plus final 2 bits. So 10 plus 2, this 12-bit. And the resolution comes accordingly, 12-bit resolution it comes. So obviously it has a good high amount of accuracy. It has very high accuracy. In my design, the accuracy was around some 300, 400 microvolts in case of if I give a DC. And with like moderate power consumption, because the comparators are very less. And here the challenge is in case of this residue amplifier or this sampling and hold block. There I was telling about these amplifiers. So this amplifier is a major design challenge here. So where this OTA are used of high gain and high UGB, high slew rate, and high CMR and OTAs are getting used there to meet our design specs. Yeah. So here you can just I think, yeah. So here you can see. So it's a basic look, my cursor I can show you. So yeah, here you can see this 1.5 bit per stage pipeline converter. So it's like each stage you can see 1.5 bit plus residue generation, 1.5 bit plus residue generation. Each stage is giving this, and from each stage 1.5 bits are coming, but actually if you we take, it will be effectively 1 bit. And this every stage it will come, and then whatever the things are there, all those things we will add stage by stage. Like from here, whatever the output bits are coming, like let's say this dn and dn minus 1 in the first stage is coming from 0 0. Now in the second stage, if it is coming some 1 1 or 1 0, third stage is coming 0 1. So we will add everything, but this addition, how it will happen, like one stage is LSB or one stage is MSB will overlap with the LSB of the preceding stage, or one stage is LSB will overlap with the MSB of the next stage. Like that, the addition will happen. And accordingly, like from 2 stage, you will get like 3 bits. That's why we called it 1.5 bit per stage. So this is the overlapping addition of so each stage will give you this 1.5 bits, and how it's the addition business is getting happened. Like from each stage you are getting like 2 bits. So first one stage LSB is getting overlapped with the second stage MSB and getting added. So like that, from 2 stages effectively we are getting 3 bits. So that's why it's 1.5 bit architecture per stage. And one more very important thing here, let's say from the first stage you are getting your number of bits at a timestamp t0, but at that time is your second stage number of the binary 2-bit output is available. It's not, we can't advance time. So what we need to do, we need to wait till our last stage of conversion. So at the last stage of conversion we'll have our data. Just before the beforehand stage, whatever it was, we will shift that data by one clock cycle before adding. The just before that one we'll shift it by 2 clock cycles. Then before that one we'll shift by 3 clock cycles. Like that, at the same timestamp t0, we will get from with the last bit we are getting. At that time, all the data will be shifted, and then it will be added all together. So it will be shift addition operation in case of this digital error correction. So this OTA again requirements are there. I think it's a whole big thing to discuss. So fundamentally, like there are concepts and all for this OTA. I think before going to there, you need to have a very good knowledge regarding basic OTA purpose and basic OTA blocks. So these are some formulas. I think I can wrap it up here because
He's asking that which ADC is best to implement to work for MTech project.
So I can answer that each ADC has an important as per application. So if you go flash ADC, it is very easy to develop, but you have to do very high speed. There is a critical challenge will come. So sigma delta ADC, you require high resolution, then your stage. So issue is every ADC has an issue, but any ADC you take, you move, that is your MTech. Any one of the ADC you take and you move as a your MTech.
Understood. So the next question is from Rajesh, and he's asking that what are the top tools of VLSI in market, and which is better, front end or back end in VLSI?
Cadence is right now is a tools which follow both back end and front end, but Synopsys also come out back end and front end, both analog and mixed signal. So based on availability of your institute or your premises, all tool has been accommodated respect to technology node on that. So typically most of people use in the academia Cadence right now.
Okay. There is one more question. Subhash is asking, sir, that is electrical and electronics qualification is mandatory to enter into the VLSI domain?
I can say partially important, but if you have a computer science or other background, there is a lot of companies come out AI chip development. They require your knowledge on that area in an algorithm perspective.
Understood. So there is one more question. Devata Hasini is asking that is this pipeline ADC, is this completely based on VLSI?
Pipeline ADC, I can say VLSI, obviously. It is a not only VLSI, is an analog and digital, both is mixed here. That's why it's called mixed signal IC.
Okay. Understood. So there is one more question I can see, and it is from Rajni. She asked, is it possible to apply AI ML in VLSI design, and how we can get data set?
No, actually, what happened when you see that he said offset, like so offset is different. Comparator has a different offset. So you train them, you take that data, and then you figure out how redundancy will add up. So there is a, because this is a one advantage. You can take multiple size, multiple voltage, multiple technology. Then you can make it your AI algorithm. So your data you can get easily through a simulation. It is not a real data, but those data can be validated in practically. So AI ML is very much applicable in our design also, but you get a easy data here.
Okay. It's a very interesting and very technical question from Lalit, And he's asking, can we incorporate high-speed ADC and DAC in one chip and tell best open source tool and softwares to design and verify?
See, open source tool is there, but if you go to the industry and this thing, still open source is the very initial stage on that. So I can say if you want to design any transceiver, there is required DAC and ADC. So not only DAC and ADC in a single chip, DAC, ADC along with the PLL and other part, it will be single chip. So you can make DAC, ADC in a single chip.
Okay. So one question here, it is from Radheshwari, and she's asking, which is in more demand, market digital or analog VLSI?
See,
Which is more in demand, market?
see,
Yes, sir.
digital is more demand, but when you understanding analog and a mixed signal domain, your opportunity of the digital also there. So because analog also cover the digital perspective on that. So that's why if you strong in analog, you obviously get in digital. But if you strong in digital, you cannot get in analog.
Okay. Sir, the last question I would like to take, Parul is asking that does VLSI design require coding?
VLSI design require coding. Obviously, as I said, digital is full of coding, verification, testing, as well as architecture. It is a full of coding. But your fundamental knowledge of circuit is required.
Okay. I want to specially thank, again, I want to thank Ashudeb sir and Pradipta sir. It's our pleasure to have you with us. Thank you so much, audience, for your active participation. Thank you once again, everybody.